Hi, I'm Aishwarya. I'm from the University of Wisconsin at Madison. Today I'm going to be presenting our work on redundancy does not imply fault tolerance. This work is an analysis of how modern distributed storage systems react to storage faults. Distributed storage systems form the basis of many modern web services like social media, ride sharing, e-commerce, etc. So it is important that these storage systems keep user data safe even in the presence of failures. And redundancy is a well-known technique for providing fault tolerance. Using redundancy, a system can tolerate failures of one or more of its components. For example, in a distributed storage system, user data is typically replicated across a bunch of nodes, and this provides fault tolerance. So the replication in the system can mask failures like system crashes, machine reboots due to power failures, or machines becoming inaccessible due to network failures. So it is well understood and expected that redundancy will provide fault tolerance. Most distributed storage systems typically depend on their local file system to store data. Although replication can mask whole machine failures, local file systems can sometimes throw partial storage faults to applications. For example, the local file system may return corrupted data on reads, and this could happen if the underlying disk block is corrupted. Similarly, the file system may return an error on read if there is an underlying latent sector error, and we call these failures as storage faults. Storage faults is a serious and prevalent problem in many deployments. Several studies and several pieces of anecdotal evidence have shown the prevalence of errors and corruptions in disks and SSDs that lead to these storage faults. So it is important for us to deal with these storage faults so that our user data is safe and available. So this naturally raises a question of how do modern distributed storage systems react to and handle storage faults? So in the first part of this talk, we are going to measure and understand how modern distributed storage systems react to storage faults. So as you might have expected, the results are not good. And so, in the second part, we are going to build a new protocol that enables these distributed systems to recover correctly from storage faults. To answer the question of how do modern distributed systems react to storage faults, we studied the behavior of 8 popular storage systems on how they react to storage faults. We picked a broad spectrum of systems implementing a variety of replication and consensus protocols, such as replicated state machines, primary backup replication, and dynamo style quorums. Our fault model is very simple. We inject only one fault into only one of the blocks in only one of the nodes in the system at a time. And these are the different types of faults that we introduce. So we introduce corruptions on reads, we inject corruptions, we inject errors on reads, and we inject errors on writes. So consider a data item that's replicated across 3 machines in a system. What would you expect if one of the copies in one of these replicas gets corrupted? And similarly, what would you expect if one of the blocks in one of these copies becomes inaccessible? So it is perfectly reasonable for us to expect that the corrupted data will be recoverable from the intact copies that are present on other replicas, and that the users never see corrupted data. Unfortunately, redundancy does not imply fault tolerance in many of the systems that we studied. We find several pieces of evidence where just a single storage fault in only one of the nodes can lead to catastrophic outcomes. Some of the catastrophic outcomes that we encountered include data loss, silent user visible corruption, unavailability of the system, and sometimes even the spread of corruption from one replica to other intact replicas in the system. And this table shows the prevalence of these different problems across multiple systems that we studied. Since we have redundancy in the system and we inject only one fault at a time, these behaviors are not something that we would expect. So our major result is that redundancy does not imply fault tolerance. So why does redundancy not imply fault tolerance? Is it due to some implementation level bugs? No. In our study, we found that there are some fundamental problems in storage fault tolerance that are common to multiple systems that we studied. And here is a preview of some of the fundamental problems that we found. So the first problem is that faults are often undetected locally by the nodes in the distributed system. And this causes harmful effects such as corrupted data being silently returned to the users. Even when systems reliably detect faults, in most cases they simply crash instead of using the redundancy present in the system to recover from the fault. Many systems do not differentiate between corruptions caused due to crashes from other types of corruptions, resulting in data loss scenarios. We find that unsafe interaction between local behavior of the node where the problem was injected and global distributed protocols can sometimes propagate corruption or data loss from one node to other nodes in the system. So this is a summary of the fundamental problems. Many systems do not detect faults. Even when they do so, crashing is the most common reaction. Crash and corruption handling are entangled in many systems, and in some systems, there is an unsafe interaction between the local behavior of the node and the global distributed protocols. And all of these systems missed multiple opportunities for recovery from storage faults using redundancy that's present in the system. So, how do we solve these problems that we found? How should systems react to recover from storage faults? We solved this for an important class of distributed systems that we call replicated state machines. These are systems that implement consensus protocols like Paxos or Raft. We design and implement corruption tolerant replication or control that help replicated state machine systems tolerate and recover from storage faults. So in the presence of storage faults, control, which is our protocol, is safe and highly available. Control achieves these reliability properties with minimal performance overheads. And we have applied control to two different systems, Log Cabin and Zookeeper, and we experimentally show control's guarantees and how control performs in the presence of failures and in the common case. So that was the introduction to the talk, and this is the outline for the rest of my talk. First, I'll talk about the measure piece on how do modern distributed storage systems deal with storage faults. So in this part, I'll first talk about our fault injection methodology, and then I'll talk about the behavior analysis of different systems that we studied, and then I'll present some results, and then I'll present the major observations that we have across multiple systems. And then in the second part of the talk, I'll be talking about the building piece. So where I'll be talking about how we make replicated state machine systems resilient to storage faults. And then finally, I'll summarize and conclude. So now let's talk about the first part of this talk, which is the measure piece. And first, I'll present some details about our fault injection methodology. So consider a distributed storage system with 3 nodes. Right? Here, a client sends a request, and to satisfy this request, the servers have to interact among each other, and they also have to interact with their local file system. Our fault model is very simple. We inject only a single fault in only one block, in only one of the nodes at a time. For example, for one run, we inject a read corruption on block B1 on server 1. Similarly, for the next run, we inject a read error onto the same block. And we inject these faults into file system user data and not the file system metadata. So our fault model captures different behaviors of different file systems. So for example, consider that these nodes run on an ext4 file system. Here, if the underlying disk block is corrupted, ext4 would return the corrupted data as is to applications, because ext4 does not have checksums for user data. Now consider a different scenario where these file systems these nodes are running on a btrfs file system. Btrfs maintains checksums for user data. So such a file system would transform the underlying block corruption into a read error. So we model this scenario as a read error in our fault model. So to inject these storage faults, we developed RFS, which is a user level fuse file system. So let's assume a read workload, right? And assume that in this particular run, we would like to inject a read corruption for block V1 on, let's say, server 1, right? RFS would read this block from the disk and it would correct B1 before returning the blocks to the server. So when we inject such a fault, we need to observe two things in the system. First, we need to observe the local behavior of the node where the fault is injected. So here we would have to observe the behavior of server 1. Locally, the faulty node, that is the node into which we injected the fault, could crash. Or maybe it could retire the operation. Or maybe it could perform no detection or recovery at all. So these are the different local behaviors that we might expect when we inject faults into a node. Now we also need to observe another important thing, which is the global effect of the injected fault. Ideally, we should not observe any harmful global effect because we just introduced one fault in only one of the nodes in the system. And there are redundant copies, right? But maybe we could encounter harmful global effects such as data loss, user visible corruption, unavailability, etc. Or maybe the system behaves correctly. That's another global effect, right? For each system that we study, we have to repeat this process of injecting fault and observing the local behavior and global effects for all the blocks on all the servers for different workloads. For example, in run 1, we introduce a fault in server 1 and observe the behavior for the fault introduced. And then in another run, for example, we introduce a different fault onto server 2 and observe the behavior for the fault introduced again, and so on. So that was our fault injection methodology. Now I'll talk about our analysis of our different systems that we studied. So before we go into that, I'm going to walk you through our behavior analysis using an example of Redis. Let me just try to give you a preview of how Redis works. Most of you may be familiar with this, but I'm just going to go through this so that we understand the rest of the talk better. So Redis is a data structure store, and simply Redis has a leader and it also has a set of followers. This is just like a simple version of how things work. And data is stored in the form of an append-only file in Redis. On a write request, the data is appended to the file and then it is also replicated onto the followers in the system. And periodically, the data in the append-only file is snapshotted and written into a Redis database file. Now, on startup, the followers need to sync with the leader. So the follower issue a sync request to the leader, and to respond to this, the leader would ship the Redis database to the followers. The followers then would overwrite their logs with the data from the leader. Now I'm going to present our experimental results for a read workload in Redis. We represent our results in grid like these. We introduce faults like corruptions and read and write errors, and we introduce these faults into either a leader or a follower at a time. And we do this for different on-disk data structures that are present in the system. These data structures are part of the on-disk file that I was talking to you about in the previous slide. For example, at a high level, the append-only file that I was talking to you about has a data part and a metadata part. So as I told you earlier, when we inject a fault, we need to observe two things, right? We need to first observe the local behavior of the node where the fault is injected. For example, here, when we corrupt the metadata in the append-only file of the leader, we observe that the leader crashes. So this is the local behavior. Now we need to observe the global effect of the fault. As Redis does not elect leader automatically, the system becomes unavailable here. So this is a global effect that we observed. Once we observe the behavior, we reason about the failure states. For example, in this case, Redis does not have checksums to detect corruption, and the leader crashes because of a failed deserialization. And since there is no automatic failover, the cluster becomes unavailable. When we inject the same fault onto the follower crashes, but it results in a reduced redundancy. We observe the same behavior for a read error as well. Now, when we corrupt the data part in the append-only file on the leader, the corruption goes undetected. However, the global effect that we observe is that the corrupted data is silently returned to the user because the corruption went undetected. So as I told you earlier, Redis does not have checksums to detect corruptions. So in this case, the leader returns corrupted data to users on queries. And moreover, the corruption ends up getting propagated to all the followers present in the system. However, the same fault, when introduced on the followers, does not lead to any harmful global effect because the followers eventually get their correct data from the leader, and the followers would overwrite the corrupted data on their node with the correct data from the leader, which is a correct behavior here. So now we repeat this for other data structures as well, and we also do this for other workloads in Redis. And we repeat this analysis and generate grids like the one that I showed you on the previous slide for the other systems that we studied as well. However, I'm not going to present those experimental results here, but I'll use the results from the behavior analysis to draw observations for the rest of my talk. So that was how we injected faults and we studied the behavior of a system. Now let's look at the major results from our study. As I told you earlier, the major result of our study is that redundancy does not provide fault tolerance. Let's consider different read and write workloads on different systems. We introduce file system faults to different on-disk structures in either a reader or a follower at a time, right? Recall that we introduce only one fault at a time, and since the data is replicated, we shouldn't be observing any harmful global effect. Unfortunately, that was not the case. We observe errors. We observe a lot of faults in these systems where the faults lead to catastrophic outcomes. For example, we observe cases where corrupted data is silently returned to the user. There are some data loss scenarios. Sometimes the system becomes unavailable. There are query failures. There are cases of reduced redundancy and so on. And these harmful global effects occur despite redundancy that's present in the system. And in most cases, these problems are not caused due to some implementation level bugs. Rather, they are caused due to some fundamental problems in file system fault tolerance, and these fundamental reasons are prevalent across multiple systems that we studied. So now I'm going to be talking about these fundamental problems in storage fault tolerance that we observed that are common to multiple systems that we studied. So the first fundamental problem that we observe is faults are often undetected locally. And these locally undetected faults can sometimes lead to harmful global effects, right? For example, let's say there is a locally undetected corruption on one of the nodes in the system. This could potentially lead to a global user visible corruption, where the corrupted data is silently returned to the user without any warning or an error message. So let's talk more about this with an example of Cassandra. Right? Cassandra is a decentralized system that follows Dynamo-style quorum replication at a very high level. And data in Cassandra is stored in the form of SS tables. Let's assume that the user data in an SS table becomes corrupted. So in Cassandra, when the compression feature for SS tables are turned off, Cassandra does not detect corruptions using checksums. So here, when there is a corruption to the user data in the SS table, Cassandra would just return corrupted data silently to the user on a read. And moreover, the read repair protocol that's in place to fix the stale versions of data ends up propagating the corruption to other replicas in the system. So even when you read from the other replicas, you would still get the corrupted data. So this leads to an observation that not detecting faults is incorrect, and many systems lack end-to-end error handling, and there is a need for end-to-end integrity and error handling in these systems that we studied. The next fundamental problem that we observed is that crashing is the common local reaction. Many systems do reliably detect faults, but in most cases, they simply crash. That is, the nodes would just simply crash on encountering a fault, instead of using the redundancy that's present on other nodes to recover from the fault. For example, let's consider an example of MongoDB. MongoDB has checksums to detect corruptions, but in most cases, a node would simply crash on detecting a corruption. And we observed such similar behaviors in Zookeeper as well. Although crashing does not result in a harmful global effect immediately, it introduces the possibility of an imminent unavailability. Moreover, since the faults are persistent, simply restarting the crashed faulty node would not help. The system would keep restarting again and again until there is a manual intervention, and manual intervention can be error prone. So it may look like crashing is the best thing to do. However, in a distributed system, there are like multiple opportunities to recover from a corruption or an error using other copies on other replicas. So crashing is not an optimal solution. So the next observation that we make is crash and corruption handling are entangled. Now let's consider Kafka. Kafka is a persistent message queue. The messages in Kafka are stored in the form of a log, and incoming messages are appended to this log. And the message in a log is also checksum. So consider that this node in Kafka crashes when it's trying to append a request to the log, which is message 2. Now, when the node comes back up, it would detect the corrupt checksum mismatch because of the partially appended entry. And then the action it takes here is to truncate the log at message 1. So as the node crashed while it was writing message 2, it was an uncommitted data. So here it is safe to truncate this message 2 that was uncommitted anyways. However, on the other hand, consider the case where all the 3 messages are safely persisted to disk, and we have acknowledged some external entity that we have persisted all the 3 messages safely onto the disk. Now assume at this point that the disk block holding message 1 is corrupted. Kafka detects this corruption using checksums, but the action it takes again is to truncate the log at message 0. Note that here messages 1 and 2 were committed data, and since the node conflated the handling of disk corruption from corruptions due to crashes, in this case the node lost some committed data locally. So to reiterate, the node treated disk corruption the same way it would treat corruption due to a crash, resulting in a data loss scenario. Developers agree that entanglement is a problem and that there is a need to disentangle crashes from corruptions and corruptions due to crashes from other types of corruptions. Next, we make an observation of unsafe interaction between local behavior of the node and global distributed protocols. Recall that the Kafka node treated disk corruptions the same way that it would treat a corruption due to a crash, resulting in a data loss. This was the local behavior. Assume that this data loss occurred on node 1. Other nodes still have the data. So Kafka maintains something called an in-sync replica set, and any node in this set is eligible to become the leader because it is supposed to have all the committed data. In this case, node 1, which truncated the log, is not removed from the set of in-sync replicas and is elected as the leader. So message reads to node 1 would result in a silent data loss. Now the leader will also instruct the followers to truncate the logs at message 0, which triggers an assertion at the followers, resulting in their crash. So writes also become unavailable. So here the unsafe interaction between local behavior, that is to truncate the log, and the lethal election protocol results in a data loss scenario and write unavailability. So in a distributed system, you need to have like a synergy, right, between the local behavior of the node where the fault is injected and the global distributed protocols. So I showed you these results earlier. Despite redundancy, we observed these different harmful global effects across many systems that we studied. I also showed you some fundamental problems across multiple systems. Now I'm going to try to tie it all together. These harmful global effects that are highlighted in red are caused because faults are often undetected locally. These effects in blue are caused because crashing is the most common local reaction. These harmful global effects in yellow are caused because corruption and crash handling are entangled, and these ones are caused because there is an unsafe interaction between local behavior and global protocols. Thus, there are some fundamental problems in file system fault handling that are prevalent across multiple systems that result in these unsafe behaviors, and redundancy is not utilized effectively to recover from these faults. So this is a summary of the fundamental problems across multiple systems. As you can see, all systems underutilize redundancy as a source of recovery. You can find more observations, results, and discussions in the paper, and I'll point you to the link to our paper in the summary of the first part of the talk. So to summarize, we analyzed distributed storage systems on how they react to single storage faults. We showed that redundancy does not imply fault tolerance in many of the systems that we studied, and a single storage fault introduced in just one node can cause catastrophic outcomes such as data loss, corruption, unavailability, and sometimes even the spread of corruption from one node to other intact replicas. And these harmful global effects are caused due to some fundamental problems that are present across multiple systems. For example, faults were often undetected locally, leading to harmful global effects. On detection, crashing was the most common local reaction instead of using redundancy to recover from faults. Crash and corruption handling were entangled, resulting in data loss scenarios. Also, there was an unsafe interaction between local behavior and global distributed protocols in many systems, which could result in spreading of harmful global effects from one node to the other. So this work was published at FAST 2017, and this is the title of our work, Redundancy Does Not Imply Fault Tolerance. And our fault injection framework, that is RSM, is also available, and here is the URL to it. That was the first part of the talk, which is the measure piece. Now I'll be presenting the second part, which is the building piece, where we build a new replication protocol that make replication state machine systems resilient to storage faults. So now let's talk about how we can recover a piece of data that's affected by a storage fault in a distributed system. Let's start with this popular and simple approach, which is to delete the data on the corrupted node and restart the node. This approach is very popular and it's also very widely used. For example, here is an answer on a forum for a question on how we can deal with corrupted data in a zookeeper cluster. So the answer goes something like this. Try clearing the data on the node and then stop the zookeeper node, then wipe the zookeeper node and maybe then restart the node and so on, right? Even developers often prescribe something very similar to this when data is corrupted for some reason. So this sounds like a very reasonable approach, right? If we delete one copy, there are several other copies, and so the system should be able to use those copies to recover from the fault. So let's go ahead, right? Let's go ahead and apply this approach and see what happens. First, we will delete the corrupted data and restart the server. Now the system was able to fix the corrupted data from one of the redundant copies. So this approach seems intuitive and it works, right? We have solved the problem. So are we done? Unfortunately, the answer is no. Sadly, fixing this problem is not so easy. If you think more carefully about this approach, it can lead to data loss, which is very surprising, right? This is surprising because we deleted the data that's present on only one node, and we still have redundant copies around. So this is not something that we would expect. For example, consider this scenario, right? Where the data item is just replicated on a bare majority of servers. So here we have 5 nodes in the system and assume that the data was just replicated onto 3 nodes in the system, right? Which is the bare majority in 5 nodes. Now, due to some storage faults, let's assume one of these copies gets corrupted. Now, according to this prescribed approach, we are going to delete the data here and then restart this faulty node. However, it's possible that the correct nodes could be now maybe operating slowly, or maybe now they have crashed. Now it's impossible that the faulty node, right, on which we deleted the data, which does not have any data now, can join with the other 2 nodes which did not see the data previously, because it may be that at that point it was operating slowly, right? Now these 3 nodes do not have this data, and maybe these 3 nodes would form a majority now. Essentially, the system has lost the data now because the majority have no idea about the committed data. So committed data is lost from the system. The fundamental reason why this approach can lead to a global data loss is that this approach is oblivious to the underlying protocols used by the distributed system. In fact, most approaches used today to recover from storage faults are oblivious to the underlying protocols used by the distributed system. Specifically, the delete and rebuild approach was oblivious to how the data is replicated and how the replicated data is updated by the system in the first place. Thus, our proposal to correctly and quickly recover from a piece of faulty data is this. The recovery approach should be carefully designed based on the properties of the underlying protocols of the distributed system. For example, the approach has to know if there is a dedicated leader that's present in the system, and what are the constraints on who can become the leader, and so on. We call such an approach a protocol-aware. So in this work, we apply protocol-aware recovery to replicated state machine systems, which is a special class of distributed storage systems. We focus on replication state machine systems for a number of reasons. First, RSMs are one of the most fundamental pieces in building reliable distributed systems. Second, since RSMs solve a wide variety of fault tolerance problems, such as distributed coordination, many systems depend on replicated state machine systems for storing some of the metadata or other problems like distributed coordination. Thus, protecting replicated state machine systems from storage faults will not just improve their reliability, it will also improve the reliability of all these other systems that are depending on replicated state machine systems. However, applying the idea of protocol-level recovery to replicated state machine systems is inherently very challenging, because replicated state machine systems provide strong data consistency and durability properties. So even a small misstep could violate a lot of guarantees. In this work, we first start by studying how current replication state machine systems handle storage faults. We do this by analyzing popular practical systems and approaches from prior research. And we analyze the popular systems using the tool that we built in the first part of the talk. And some of the results I also presented some of the results in the first part of the talk. Our major findings are that most practical systems do not use any protocol level knowledge to recover from faulty data. We also find that although some approaches try to use protocol level knowledge, they do so incorrectly. Consequently, many approaches lead to safety violations, or they are sometimes unnecessarily unavailable. Whereas an ideal approach should not suffer from any of these problems. Our solution, control, is such an approach. It exploits the properties of the underlying distributed systems. Specifically, it exploits the properties of replicated state machine protocols. And in the presence of storage faults, control guarantees safety and high availability with low performance overheads. We have applied control to two systems, log cabin and zookeeper, and we experimentally show control's guarantees and show that control only adds little overheads to provide these guarantees. So that was the introduction for the second part of the talk. Now I'll be talking about, here's the outline for the rest of the second part of the talk. So first I'll present a primer on replicated state machines, and then I'll present some of the current approaches to handling storage faults in replicated state machine systems. And then I'll be talking about our solution, which is corruption tolerant replication or control. And then I'll present some evaluation results. So now I'll talk about replicated state machines. So let's start with some background on replicated state machines. Replicated state machine is a paradigm to make a program or a state machine more reliable. So the key idea behind the replicated state machine is to run this program on many servers. And if the servers all start from the same initial state and then they process the same sequence of inputs, then they'll essentially produce the same outputs. And one of the important properties of a replicated state machine system is that the system should be available and produce correct results if a majority of servers are up and are able to communicate with each other. A consensus protocol such as Paxos or Raft ensures that the individual state machines process the input commands in the same order. With that, let me now briefly explain how the replicated state is updated in a replicated state machine system. So the command is submitted by the client, and the commands that are submitted by clients are stored on a replicated log. Each node in the system maintains this piece of replicated log. Typically, there is a single node in the system that's called the leader, and this is the node to which the clients would talk to. And then there are a bunch of followers. Let's say a client wants to execute this command C, right? The client would send this command to the leader, and the leader would then append this command to its local log, and it will also replicate the command to the followers. The followers also safely write the command to their log and respond back. Once a majority of servers have responded, the leader executes the command and returns the response to the client. At this point, the command is considered committed and should not be lost. Periodically, this log is also this in-memory state machine is also snapshotted to the disk, and the log is garbage collected on all the servers. Because we are interested in dealing with storage faults, we also need to carefully understand the different persistent structures that are maintained by the storage system. So here in a replicated state machine system, as I already talked to you about in the previous slide, there is a log and then there is a snapshot. Apart from these two data structures, there is also another data structure, which is the meta info, which is a crucial persistent structure that contains wild-type metadata information, for example, information regarding voting. And one important aspect of this meta info is that it contains information that's specific to a single node, and so it cannot and should not be recovered from redundant copies, unlike logs and snapshots. And all these replicated state machine persistent structures could be affected by disk corruptions or latent sector errors. So thus, upon a read access, depending on the local file system in use, the application could receive corrupted data or it could receive an error. So that was a background on replicated state machines. Now I'll talk about some of the current approaches to handling storage faults. So as I told you earlier, we perform our analysis by studying practical systems, which is from the first part of the talk, and then also analyzing approaches from prior research. And through our analysis, we classify the approaches into two categories. The first category is the protocol-oblivious one, where approaches do not use any protocol level knowledge. The second category is the protocol-aware approach, and these approaches use some knowledge about the underlying protocol that are present in the system, but they do so incorrectly or ineffectively. There are three different types of approaches in that class. Now, to illustrate the different approaches, I'm going to first walk you through to a couple of approaches. Let's start with a simple one. In this approach, the system, which is the crash, so in this approach, the system uses checksums and catches IO errors. And the action that it always takes when it encounters such problems is to crash the node upon detecting a fault. And this is a popular approach which is used widely in many practical systems. Although this approach is safe, it can lead to poor availability. For example, let's say a couple of nodes have already failed, and then there is one node in which there is a single storage fault present in its log, maybe. Now it's possible that this node, because this node has a storage fault, the storage system crashes this node, and then now because the other two nodes are also down, the storage system as a whole would become unavailable. Now consider this other case, which is maybe unlikely, where there is a single storage fault present on different portions of the data on at least a majority of nodes. This could also result in an unavailability. Note that crashing and restarting the node would not just help, because even if you restart the faulty node, because storage faults are persistent, this node would remain in a crash restart loop. So to bring this node out of this crash restart loop, we need some sort of manual intervention. And manual intervention can be error prone and could lead to safety violation. For example, the delete rebuild approach is a sort of manual intervention approach, right? Where you manually deleted the data that was present on one of the nodes that had this corruption, and that resulted in a global data loss. So manual intervention can sometimes be faulty. So here is another interesting approach. In this approach, upon detection, the node discards the faulty portions of data and it continues to operate, which sort of improves the availability, unlike crashing. However, we find that this approach can lead to safety violations. For example, consider this state where you have 5 nodes, S1 to S5, and then you have the logs on all of these nodes, and 3 of these nodes have committed entries A, B, and C. And let's assume that S1 is currently the leader. Now, let's say that the first entry on S1 gets corrupted. Upon detection, S1 truncates this faulty entry and all subsequent entries that are present in the log. Let's assume that at this moment, maybe S2 and S3 crash. And furthermore, now it's possible that S1, S4, and S5 form a majority, and then they elect S1 as the leader among themselves. Now we have a majority of nodes which do not have any idea about the committed entries A, B, and C, and so the system has silently lost those committed entries. Furthermore, it's possible that this new majority now could commit new entries in this place of the old entries and can override the correct old entries. Now even S2 and S3 recover from the crash, their logs also would be overwritten. So the key reason behind truncating faulty data is the entanglement of crashes and corruptions I talked to you about in the first part of the talk. That's the reason that these systems truncate the faulty portions upon detection. So that was a couple of current approaches, and here is the summary of all the approaches that we looked at. So at a high level, as I told you earlier, there are two classes of approaches. One is a protocol-oblivious class, and another is a protocol-aware class. And these are the different approaches that fall in both of these classes. And we evaluate these approaches across multiple axes: safety, availability, how they perform in the common case, how they perform in the recovery, whether they require some manual intervention or do they require extra nodes, and how complex or is it to implement that approach, and so on. At a high level, neither of the none of the approaches, right, provide both safety and availability at the same time. And many approaches require some sort of manual intervention, and none of the approaches recover fastly. And then some approaches also have high complexity. Control, on the other hand, aims to provide all these properties, and we show how we achieve these properties in our system. Now let's talk about our approach, which is corruption tolerant application. Here is a high-level overview of how control works. So how control has two critical components. First is the local storage layer, which manages the local data, and its main goal is to reliably detect faults. Second, we have the distributed recovery layer, which recovers the faulty data from redundant copies that are present on other servers. And both these layers exploit replicated state machine knowledge to correctly and quickly recover from storage faults. Before going into the details of how corruption tolerant replication works, I'll briefly describe our fault model. Our fault model includes standard failures such as crashes, network partitions, etc. And we augment these common failures with storage faults, where the data blocks of different replicated state machine structures could be faulty. Next, the file system metadata blocks of the persistent structures could also be faulty. For example, the inode of a snapshot or a log could be corrupted. Under this fault model, control provides the following guarantees. First, committed data will never be lost. So as long there is one intact copy of the data item that's present in the system will be able to recover the data item. So in the unlikely case where all the copies are faulty, the system will correctly remain unavailable. Second, control will provide the highest possible availability. Now let's talk about control's local storage layer. The main function of the local storage layer is to detect and identify which portions of the data are faulty. For this, the storage layer uses well-known techniques such as checksums and handles errors or file system errors properly. Next, the local storage layer needs to disentangle crashes and corruptions. As I told you earlier, the underlying problem is that a checksum mismatch could either due to be a disk corruption or it could be due to a system crash. And the storage layer needs to distinguish these two cases. Otherwise, as I showed you in the earlier parts of the talk, safety could be violated. And we would like the storage system to perform these functions with very little performance and space overheads. So for the rest of the talk, I'll not be talking about controls local storage because of the interest in time. And I'll be talking about the distributed recovery. So there are two parts to distributed recovery. First, we need to recover the logs, and logs might be corrupted, or snapshots could be corrupted, and we need to recover the snapshots from other nodes of the system. However, for the purpose of this talk, I'll be focusing on the distributed log recovery. So before we look into how the log recovery works, here are some of the properties of RSM systems that control exploits. So the first property that control exploits is that many replication state machine systems or consensus protocols are leader based. That is, there is a single dedicated node in the system that acts as a leader, and all the updates in the system flows through this leader. And then the second property that we rely upon is that of an epoch. Consensus protocols partition time into logical units that are called epochs. So for any given epoch, only a single leader is guaranteed to exist. And further, a log entry is uniquely identified by the index and the epoch in which it was appended to the log. Finally, replicated state machine systems have the leader completeness property, which means that the leader is guaranteed to have all the committed data that's present in the system. And these properties apply to many systems and protocols that we studied. Specifically, these properties apply to consensus protocols like Raft and ZAP and most implementations of Paxos. And control exploits these properties to perform its recovery. So as a first step, control simplifies log recovery by decoupling the recovery of followers from the recovery of the leader. Fixing the followers is fairly simple because faulty entries on the followers can be just fixed by the leader because the underlying protocol guarantees that the leader will have all the committed data. For example, consider this case where leader has all the committed entries and all the committed entries are intact on the leader, whereas there are some corruptions in the followers log. Now the follower could just specify the epoch and index of the corrupted entry, and then the leader could just give the correct entry to the followers. So this is how you can fix all the corruptions on all the followers if the leader's log is intact. The trickiest part here is to fixing the leader's log. Let's start with a simple case. In this case, followers will have the entry that is corrupted on the leader. This is the simple case that we are going to assume. Let's consider this state where the leader, the last entry in the leader is corrupted, whereas you have two followers that have this corrupted data, whereas the other two followers have the correct data for the data that is corrupted on the leader. Now the leader could just specify the index and epoch of the entry that is corrupted, and the followers would just send the correct item to the data through the leader. Now, once the leader is fixed, fixing the followers is fairly straightforward. We could just use the data that's present on the leader to fix the followers. However, there is one tricky case in fixing the leader's log. So consider this case where an entry in the leader is corrupted and none of the followers have that entry. Or consider this case where the entry is corrupted on the leader and there's just one follower that knows about this entry, but maybe it's down or partitioned from the rest of the system. So the key insight here in recovering the leader's log is to separate committed entries from uncommitted ones. That is, one needs to recover committed entries always, but some entries that are not committed can be safely discarded. And discarding entries that are not committed as early as possible is important for improved availability of the system. So the key idea here is to determine the commitment of a particular log entry. So the leader will query for a faulty entry, and if a majority of nodes say that we do not have a particular entry, then that entry must not be a committed entry. It must have been an uncommitted one. So the leader can safely discard that entry and continue operating normally. For example, consider this case where only the leader's log has a particular entry and that entry is corrupted. The leader asks for this corrupted entry and all the followers respond that they do not have this corrupted entry. So the leader can discard this faulty entry and continue operating normally. If this entry is committed, that is, if the entry that is corrupted on the leader is committed, then at least one node in this majority would have the correct entry because of the basic property that a committed entry needs to be present on at least a majority of nodes in a replicated state machine system. So the leader can fix its corruption using the response from the followers. For example, consider this case where the leader's last entry in the leader is corrupted and two of the followers have this entry because this entry is a committed entry. And so the leader will get a response in this scenario and it can fix its log easily. Now it's possible that majority of nodes do not have this entry while one of the node in the system has the correct entry. And either of these could happen and both of these are correct. Either, for example, one of the followers could respond with the correct entry, and in which case the leader could fix its log, or a majority of nodes say that they do not have the entry, and both of these are correct. So either the leader can fix its log or it can discard, and how it happens would depend on the order of these two scenarios. For example, if 1 happens before 2, then the leader would fix its corrupted entry using the correct entry from the follower. Whereas on the other hand, if 2 happens before 1, then the leader would discard its correct entry. And note that both of these orders are safe. There are more details in the paper on how we recover snapshots, how we do meta info recovery, and how we handle file system metadata faults. And then there are some other interesting scenarios to log recovery as well. But again, I'm not going to be talking about that here because of the interest in time. However, I refer you to our paper, and this is the whole details about our paper, which appeared in FAST 2018. Now I'll evaluate our system. So as I told you earlier, we implement our idea in two systems, Log Cabin, which is based on Raft, and Zookeeper, which is based on Zab. And we ask two questions in our evaluation. The first question that we ask is, how does control recover faulty data? Does it recover the data correctly? Does it enable high availability, and so on? And the second question is, how much performance overheads does control induce because of this additional reliability? First, I'll show you some reliability experiments. Here is one example. So in this example, we inject corruptions and errors on file system data blocks of the log, and thus many entries or maybe partial entries in the log could be faulty. And here are the results of this experiment. In the original system was that does not have control, can be unavailable or unsafe in 30% of the cases when we introduce corruptions, and it's unavailable in many percentage of the cases when we introduce errors. Control, on the other hand, is always safe and available when we introduce corruptions and errors into the data blocks. That was just one of the reliability experiments that we did. In our paper, we also do perform other reliability experiments where we introduce corruptions into targeted entries, and we introduce like all possible combinations for thoroughness. And then we also introduce corruptions and errors in the presence of nodes that are lagging or maybe nodes that have crashed. And then we also introduce corruptions into snapshots. And while doing so, we have like all possible scenarios where like some of the log entries may be garbage collected, or maybe some log entries and some snapshots could be corrupted, and so on. And then we also introduce like file system metadata faults, where we introduce the effect of having a file system metadata fault, like having a file that is unopenable or having a file that's missing, and so on. And the high level result of all these reliability experiments is that in the original system can be unsafe or unavailable in many cases, whereas control versions, on the other hand, is always safe and available. And it is in the corner case that all the copies are faulty, control remains correctly unavailable. So now I'll show you some update performance overheads that are introduced by control. So the workload that we use here is to insert 1K entry repeatedly and system also takes snapshots in the background. Here are the results for Log Cabin on the left and Zookeeper on the right. We show the results for the original system that does not protect itself from storage faults, and the control version of the system, which adds more reliability and protects the system from storage faults. The y-axis shows the throughput, so higher is better, and in the x-axis we vary the number of clients. And we show this experiment when the nodes, the data on the nodes are stored on an SSD. So here are the results. So the result is that control adds only little overheads. It closely matches the performance of the original system, and it adds only little overheads for the additional reliability that it provides. The key reason behind this additional overhead is because control writes some additional information along with each entry in the local storage layer. And however, note that this is very little, just 4%, and in on SSDs, and in the worst case on a disk, it could be 8 to 10%. However, note that this is a workload that is consisting of all writes, and so it's a worst case workload. If a workload has a mix of reads and writes, this overhead would further go down. So that brings us to the end of the second part of the talk. So to summarize the second part of the talk, recovering from storage faults correctly in a distributed storage system is surprisingly tricky. Most existing recovery approaches are protocol-oblivious. That is, either because of that they cause unsafety or they have low availability. So to correctly and quickly recover from a storage fault, an approach needs to be protocol aware, and control, which is corruption tolerant replication, is one such protocol aware recovery approach for replicated state machine systems. And control guarantees safety and provides high availability, and it adds only little overheads when compared to an unmodified system which is not protected in storage faults. So that brings us to the end of the two parts of the talk. Now I'll finally summarize the entire talk and make some concluding remarks. To summarize the first part of the talk, we measured how current distributed storage systems react to storage faults, such as corruptions and errors. And the main result of that part was redundancy does not imply fault tolerance. We saw how just one problem that we introduced into one of the nodes in the system could lead to catastrophic outcomes such as data loss, unavailability, spread of corruption from one node to other nodes, and so on. And we also saw how these problems were caused due to some fundamental root causes in storage fault handling, which was common across multiple systems that we studied. And to summarize the second part of the talk, we built a new recovery protocol for replicated state machine systems that we call control. And control is safe and highly available, and it only adds little overheads when compared to an unmodified system. To conclude, even the seemingly obvious things that we take for granted in a distributed system, such as redundant copies will help recover from bad data, or more generally that redundancy will provide reliability, are sometimes surprisingly hard to achieve. And this is shown by our work. In the first part of our talk, we showed how many systems currently are not resilient to storage faults. In the world of layered stacks that run on commodity hardware where faults are common, we cannot afford not to detect faults. In a distributed system, there are other unavoidable causes like power failures or network failures where nodes become unavailable. So in cases where automatic recovery is possible, we shouldn't just simply crash the nodes, and we should try and use the redundancy that's present on the system to recover from faults. Protocol awareness is the key to utilizing redundancy to safely recover from bad data. That is, the approach needs to be aware of what's going on underneath the system. However, our work on control is only the first step. While we have applied protocol-aware recovery to replicated state machine systems, other classes of systems still remain vulnerable. And we believe that the protocol-aware recovery approach can be applied to these classes of systems as well. With that, I will conclude. So for more information regarding our work, please visit our project page and our publications web page. With that, I'll conclude the talk, and I'll be happy to take more questions.
Thank you, Aishwarya, for the great talk.
Thank you.
Yeah, I think it's pretty much amazing what you did.
Thank you.
Are you ready for the questions?
Yeah, sure.
Okay. So the first question I think anyone would ask you after everything we have heard. Yeah. By the way, maybe I should say that your first research you mentioned in your talk started in 2017. So it's almost 5 years. Yeah. And the very question that everyone would want to ask is, Do you know how the situation changed since then? Since you did
Yeah,
this research and found all those
yeah,
inconsistencies and weak behavior.
yeah, yeah. I guess that's a great question to ask. And I would say that we did report like some of the problems that we found to the different systems, and we filed bug reports. And I guess like the easy ones, like fixing the bugs, some of them have been fixed. For example, like the one of the write unavailability bug that we encountered in Zookeeper, I believe it has been fixed. I guess like fixing bugs is probably like the easier part, where you found a bug, you know this is the root cause of the bug, so you go ahead and fix it. But I think doing making these systems tolerable to storage faults is probably like a more involved thing. And I'm not sure like what's the state of the art is right now. And yeah, I would be happy to go back and do the study again, like let's say in a couple of more years, and see whether I'm able to see the results that we saw sometime back. But yeah, I don't have like a definitive answer for that. But I can say that like some of the bugs that we reported have been fixed.
Okay. I wanted to ask you, do you know, are you aware of maybe of systems that adopt nowadays your control protocol or control style protocols to handle the fault tolerance for the state machines that implies consensus based?
Yeah, so I'm not aware of systems that adopt this approach, but we went ahead and implemented this control in two popular systems, Zookeeper and Log Cabin, and we hope that in the future other systems would also adopt this approach. And in the future, we hope that we can look at how we can apply this protocol level recovery and control side uh, corruption tolerant replication to other classes of systems beyond replicated state machines.
Okay. Also, I'm curious how everything began at the start. Is it you who came up with the idea of testing those systems, or it was funded research, or how is happening such
Yeah,
research to be bring in life?
yeah, I think like that's an interesting question. So I guess it all started back in 2015. So our group, the research group that I work in, uh, they are famous for local storage. So they work a lot on local storage, and they a lot of previous other researchers from our group have worked on looking at such problems like what happens in the presence of corruptions, what happens in the presence of storage faults in local storage stack, like file systems or local databases and so on. And we thought like, okay, let's look at this in a distributed system. We started looking at one system, which was Cassandra, and then we found this problem where corruption was sort of propagated to other nodes in the system. And we thought, okay, this is an interesting result. Let's do like a full-blown study. Let's sort of build a tool. Let's study more systems and see what's happening. And then what we found is, obviously we found a lot of implementation level bugs that could be easily fixed, right? But when you remove these bugs, what remains is what is interesting. And then when we looked at what remained after we removed those bugs, we saw these fundamental problems that were common across these multiple systems. And then we saw, okay, these are the fundamental problems, and this is how one fundamental problem is causing this fundamental cause. For example, like in one system, the fundamental problem was that crashes and corruptions were entangled, and then when this interacts with the global protocol, it leads to different harmful global effects. And we saw that this fundamental thing was common across a lot of systems, and it is common to any log-based system. So that's how this project came about.
Yeah, it's pretty much interesting. I'm curious, did you expect anything like that, that you will discover such a big issue among all of the industry-wide open source software?
Yeah. So I guess like before that, right, I want to say that most of these systems are reliable, right? They handle a lot of things correctly. For example, in the presence of uh, whole machine crashes or in the presence of network partitions, a lot of these systems are reliable already. It's just that in the presence of storage faults, maybe these systems are not doing the best that they could. I guess that's probably the takeaway. I would not say that these, definitely not make a comment that these systems are broken or anything, right? Like a lot of these systems do handle many of the failure cases really well. For example, they handle crashes and network partitions really well. And even in the presence of storage faults, some of them do have checksums to detect them, or they conservatively crash. But I guess like the main takeaway is maybe these systems are not doing the best that they could in using the redundancy to recover from the faults, right? And yeah, so I guess like to answer your question on whether we expected to find these problems, I guess we did not expect to find this problem. So it started like as a fun course project that I did back in my first year of grad school. I just like manually corrupted some data files on Cassandra and so see if I can find some problem. And then I found some interesting problems. And then I did this thing for other systems, and we developed a tool to do this automatically on a lot of systems. And we were surprised that we found these problems. And I guess like the more surprising thing that we had is also how there were these fundamental problems that were common to multiple systems.
All right, thank you very much. We are kind of out of time. Sorry for these hard limits.
Yeah.
Thank you, Aishwarya, and thank you, Ivan, for supporting with Q&A. I guess see you there in Zoom link. Please follow that one, and see you around. Bye-bye.
Yeah, bye.
Thank you. Bye-bye.
Yeah, thank you so much for this opportunity.